Welcome to Number Theory. Today, we are going to explore one of the most beautiful and surprising results in all of mathematics, the prime number theorem. If you have ever wondered whether prime numbers follow a hidden pattern as they stretch out toward infinity, you are in the right place. Let us dive in and uncover the secret rhythm of the primes. To begin our journey, imagine walking down a very long, endless highway and looking for gas stations. At the beginning of your trip, you see a gas station almost every single mile. But as you drive further away from the city, the gas stations become rarer and rarer, with massive empty gaps between them. Prime numbers behave exactly like these gas stations on the number line. When you look at small numbers, primes are everywhere. But as you count higher into the millions and billions, the gaps between prime numbers get larger and larger. The overall density of primes slowly decreases. For centuries, mathematicians wondered if there was a hidden rule predicting exactly how these numbers thin out. Now that we understand how primes thin out, we need a way to measure them. To do this, we define a special tool called the prime counting function. It is simply a tally of how many prime numbers exist up to a certain number, and it is written using the Greek letter pi. Do not confuse this with the geometry pi used for circles. Here, pi of x just means the total count of primes less than or equal to x. For example, pi of 10 is 4 because there are exactly 4 primes less than or equal to 10. 2, 3, 5, and 7. This function is the foundation of our theorem. This brings us to the prime number theorem itself, which gives us a mathematical formula to estimate the number of primes up to any given point without counting them one by one. The formula states that pi of x is asymptotic to x divided by the natural logarithm of x. Let us break down these symbols. Pi of x is our exact prime count. The tilde symbol means is asymptotic to, which tells us the two sides become practically equal as x grows toward infinity. The denominator is the natural logarithm of x. As x increases, its natural logarithm also increases, which mathematically forces the fraction to grow slower than x itself. This perfectly models our earlier observation that the density of prime numbers slowly decreases. Now that we have seen the basic formula, let us look at the most rigorous way to write the prime number theorem using calculus. We use a limit equation. It tells us that if we take the true count of primes, pi of x, and divide it by our estimate, x over the natural logarithm of x, the ratio will get closer and closer to exactly 1 as x approaches infinity. The symbol lim stands for limit, meaning we are looking at the behavior as x gets endlessly large. It is crucial to understand that while the absolute difference between the true count and the estimate might still grow, the percentage error shrinks to zero. The bigger the number you are looking at, the more accurate this estimation becomes. Before we move on to calculations, let us see this relationship visually. The graph you are looking at proves what the math just told us. On the horizontal axis, we have our number range, and on the vertical axis, the number of primes. The jagged blue steps represent the actual exact count of primes. Notice how it jumps up by 1 every time we hit a new prime number? The smooth red dashed line is our mathematical estimate, x divided by the natural logarithm of x. See how it flows right through the middle of those steps? As we move further to the right, the red line becomes an increasingly reliable guide for the blue steps. Now that we have a visual understanding, let us see how well the prime number theorem works for a relatively small number. We want to estimate how many prime numbers exist between 1 and 1000. We start by identifying our upper limit, so we set x equal to 1000. Next, we plug this into our estimation formula, giving us e equals 1000 divided by the natural logarithm of 1000. To solve this, we first need to evaluate the denominator. Using a calculator, we find that the natural logarithm of 1000 is approximately 6.908. This continuous decimal value will help scale our discrete prime count. Continuing with our calculation, we now substitute this logarithm value back into our fraction. We divide our total range of 1000 by our logarithmic scaling factor of 6.908. This division mathematically thins out the total count. The calculation gives us approximately 144.7. Since we cannot have a fraction of a prime number, we round this to 145. The actual exact number of primes up to 1000 is 168. While 145 is not perfectly accurate, it gives us a solid ballpark figure. The error here is about 14%, which is expected for a relatively small number. Since the theorem promises better relative accuracy for larger numbers, let us test it on a much larger scale. We will estimate the number of primes up to 1 million. This is a much more realistic scenario for modern computing applications. We follow the exact same approach as before. We set our new upper limit x to 1 million. This represents a much larger search space where the mathematical laws governing primes become more dominant. We set up our approximation fraction, placing 1 million in the numerator and the natural logarithm of 1 million in the denominator. Continuing our estimation for 1 million, we evaluate the denominator. The natural logarithm of 1 million is approximately 13.815. Notice something fascinating here. Even though our x value grew by a massive factor of 1000 compared to our first example, the logarithm only doubled. This incredibly slow growth of the logarithm is exactly why primes thin out so slowly. It perfectly captures the stubborn persistence of prime numbers. We now substitute this value back in, setting up our final division of 1 million by 13.815. For the final step of our mathematical approximation, we divide 1 million by our newly calculated natural logarithm. This yields approximately 72,385. So the formula estimates there are about 72,385 prime numbers up to 1 million. The actual exact count is 78,498. The error has now dropped significantly to about 7.7%. Just as the limit equation predicted, as we look at larger and larger numbers, the relative error shrinks and the approximation becomes a much better reflection of reality. So we have proven that this approximation works beautifully. This brings us to why it matters in the real world. The prime number theorem is not just a neat mathematical trick, it is a foundational pillar of modern computer science. In the real world, prime numbers are the secret keys used in cryptography, specifically in systems like RSA encryption that secure our emails and bank transactions. To generate these secure keys, computers need to find massive prime numbers, often hundreds of digits long. The prime number theorem tells computer scientists exactly how many primes exist in those massive ranges, guaranteeing that there are always enough primes available to keep our data safe. To wrap up our lecture, let us review the key takeaways. We learned that while individual prime numbers appear randomly, their overall density follows a strict, predictable rule governed by the natural logarithm. By using the simple formula, x divided by the natural logarithm of x, we can accurately estimate the number of primes up to any massive limit. We also saw that the relative accuracy of this estimate improves as numbers grow larger. This beautiful connection between discrete counting and continuous logarithms remains one of the greatest achievements in mathematics. You now understand the fundamental law governing the distribution of primes.